Hi, welcome back. This is David Ingles. We're going to do example 3 now of magnetic circuits with nonlinear materials. In this example, we'll use the guess and check method to find the operating point for a simple core gap circuit. The structure is the same as the previous examples, but the numbers are a little different. We have a magnetomotive force of 500. We'll use a core made of SAE 1020 low carbon steel. The gap is the same at 5.5 millimeters. The length of the core is also the same, 16 centimeters, and the gap area and core gap are still 3 times 10 to the minus 3 square meters. The process for the guess and check method moves something like this. We have to assume a B field. We have to take a guess at that. And we use this B to find mu. And this is from the BH curve. Then we use mu to find B. Use B to find mu, again, from the BH curve, and repeat as necessary until convergence. So if we have a BH curve, looks something like this. We'll take a guess at a value for the magnetic field. If we were at that magnetic field, we could determine the permeability. We can then use that permeability for the core to determine the new magnetic field. That should take us to a new point on the curve, and we repeat the process. And each time we do this process, we should get closer and closer to the actual value. Now, the guess. The guess could be just about anything. Two popular or easy choices are somewhere on the linear phase. Midway up the linear phase is fine. Another choice is to assume the gap is the dominant reluctance, i.e., use the y-intercept of the load line. We'll use the second method here, though either one would work. So, if we ignore the core, seems a strange assumption given that that's really the problem here, but we can say that B is equal to Ni over L of the gap times mu naught, or 500 times 4 pi times 10 to the minus 7 over 5e minus 4. That gives us 1.256 Tesla. So we'll look at our BH curve. 1.256. 1.2, 1.3, 1.3 is about there, 2.5 is about there, so it's somewhere about there. 200, 400, 600, 800, 900. So our first mu value, mu from BH curve is equal to 900 and the units from mu have just escaped me. Right? Sorry, I've got that wrong. H from BH equals 900 ampere turns per meter. And then we can calculate mu as b over h, or 1.256 over 900. That's 1.4 times 10 to the minus 3. So we'll go, and now we can use this mu to find b again. Now we have to include both. So we have the reluctance of the core being 0.16 over 3e minus 3 times 1.4 times 10 to the minus 3. That is equal to 3.84. Reluctance of the gap is 5e minus 4 over 3e minus 3 times mu naught. That is 1.326e5. We'll combine these to determine the flux as 500 over where 1 are sums of the reluctances. Continuing, this gives us B as flux over area of 2.9 E minus 3 divided by 3 E minus 3, 0.975 Tesla. We then repeat, we go to our pH curve, 0.975, 0.8, 0.9, 0.975, there, here, 2, 4, I'm going to guess 530. H is 530. And from the BH curve. We're not going to get many digits of precision this way, but okay, now we have to find mu. B over H, 975 over 530. 1.8 E minus 3. We find the reluctance of the core, once again, 0.16 divided by 3E minus 3, 1.8 E minus 3, 2.96 E4. The reluctance of the gap hasn't changed, it's still 1.326 E5. Find the flux over the sum of the reluctances, and that gives me 3.07 E minus 3. And I find B as the flux over the area. Now, that is close enough to that for this method. So we know that the operating point is somewhere around here. Now, just as a check, we can try the load line method. Let's have a look at how that would go. Well, the y-intercept, we know already, is 1.256 Tesla. The x-intercept is the H field if we ignore the gap. and that's 500 over 0.16, or 3125 ampere turns per meter. 3125, 2468, about there. 1.256, we already have. There. Got our ruler. And it's pretty much bang on. And I've done this on the Excel, and we get 1.04 using the load line method. So our guess and check method got us there, and both methods work, though the load line method is quicker when you can use it, but you can't always use it.